Now let's look at the properties of the probability density function, the PDF. The first one, by definition, since the PDF is defined as the derivative of the CDF, and since the CDF is a non-decreasing function, its derivative, the PDF, must be a non-negative function. So for any value of the parameter x, the PDF value is going to be non-negative. Now here, you have to make the distinction between the characteristics of the CDF and the characteristics of the PDF, because the CDF by definition is a probability. So it's confined in the interval from 0 to 1, and it's non-decreasing because it's cumulative of probabilities. On the other hand, the PDF, it's non-negative, as we have just seen, but it's not a probability, so it can exceed 1. It can also decrease because it's not cumulative. It's the derivative of the CDF. So it could be a decreasing function at times. But the essential point here is it can exceed 1, but it cannot fall below 0. Okay, it's a non-negative function. Second property is again based on a property of the CDF, and it stems from the fundamental theorem of calculus for two values a and b, where a is less than b. Recall that the probability of the random variable being between a and b, where b is included but a is excluded, is given by the difference between the CDF values at b and a. And using the definition of the PDF and the fundamental theorem of calculus, since the PDF is defined as the derivative of the CDF, we can write this difference as the integral from a to b of the PDF. This is a very essential point, and when you want to compute the probability of such an event, a less than x less than or equal to b, if you have the CDF, you take the differences at points a and b, or if you have the PDF, you just integrate, meaning you compute the area under the PDF from a to b. So for instance, if you have a PDF, let's say something like this, from a to b, this area here is going to give you the probability that the random variable is between a and b. But recall, in the most general sense, this is for a strictly less than x less than or equal to b. Okay, so the integral from a to b of the PDF gives this probability. Similarly, if you let a here go to minus infinity, now this will go to 0, as we have seen by the limiting properties of the CDF. And what you will be left to is just this. So if you take the integral of the PDF from minus infinity up to parameter x, and be careful, I'm using a different integrating parameter here, not x, because x appears in the integral limits. Therefore, I'm using t inside. And this integral will give you the CDF at point x. So this is a little bit analogous to the relationship between the CDF of a discrete random variable and its PMF. Recall that if you have the PMF of a discrete random variable, to compute the CDF of that random variable at parameter x, you just add up the PMF values where the parameter is below and including x. Now, instead of addition, we have here integration, because due to the characteristics of continuous random variables. And finally, if you also let b here go to infinity, plus infinity this time, or maybe you can take the limit of this as x goes to plus infinity, what you get is the integral of the PDF across the entire real line, which includes the sample space, obviously, which should give you 1. So any PDF function, something like this, I don't know, the area under it in its entirety should be 1. So any function that doesn't have an area, or a total area of 1 under it, cannot be a PDF. So for a function to be a PDF, first of all, it must be non-negative. And secondly, the area under that function over the entire real line should be 1, because this is equal to the probability of the entire sample space.